Hey guys, last time on 4.5 we talked about the derivative of block functions. More specifically, we talked about the derivative of ln and other bases. So for example, the derivative of ln of x equals to 1 over x. Okay, and if you were to have like some other function rather than x, for example, let me write in pink. Say if you're gonna have like an inside function, I don't know, like 3x minus like 5 in there, then the derivative of this function in here is that first you have to flip like whatever inside of ln out. So it's going to be like 1 divided by 3x minus 5, right? And then on top of that, you have to multiply it by the chain rule. So then the chain rule, you have to take the derivative of the inside. Or you can set up the table of, inside and outside function, just like how we did it in the chain rule in the past. And then the derivative of this one will be 3. Okay, so then the final answer of this one, it would be 3 divided by 3x minus 5. Okay, so let me put a 3 in here. And just really quick, this 3 in here is for the chain rule, and then this one in here, we flip it because that's the derivative of ln in general. Okay, and another thing I want to emphasize in here is that we also learned about the change of base formula in there, just so it's easier for us to calculate log functions in the calculator. Okay, so for example, if I were to give you something like log 2 of 3, then to calculate the value of it, well, you can input into the calculator log 3 divided by log 2. Okay, so the bigger number will go into the top, and then the smaller number will go into the bottom. Okay, and then similarly, if I give you something like, I don't know, log base 4 of 2, for example, then what you're going to do is that you're going to do ln 2 divided by ln of 4. So the bigger in size will go on top, and then the smaller number in size will go into the bottom, right? And as you can see in here, it really doesn't matter whether you use log or ln's. Okay, they should all give you like the same answer in the calculator. If you don't trust me, try it out on your calculator to see if you're gonna have the same result for ln or for log. Okay, and another key formulas that we also learned from the last section, they are about the derivative of all the other like bases log, right? So say if we're gonna get something like, I don't know, log 2 of x, the derivative of its function is, first of all, we're gonna flip it, so we're gonna get like 1 divided by x, and then we have to multiply it by 1 divided by ln of 2. Okay, so make sure that you have this part, okay, because this one is very important, because the 2 in here cannot be just forgotten. Okay, and another formula that we also learned in the past section is about a to the x. So for example, if I give you something like 3 to the x and I ask you to take the derivative of it, well, you're gonna tell me that it equals to 3 to the x, like the same thing itself, but then you multiply it by ln of 3. Okay, and I told you guys, like, if you have like a fraction, then you're gonna multiply the ln as a fraction, and if you don't have a fraction, then you're gonna just multiply ln as not having a fraction. Okay, so then you don't have to make sure you don't have like a mix and match between like fraction and non-fraction functions. Okay, so that's about 4.5. So let's talk about 5.1, antiderivatives and indefinite integrals. Before we get into that, this one, the table in here is a quick review of all the derivatives that we learned so far. We have like constant rule, general power rule, constant multiple rules, some indifferent rules, also product rule, chain rule, and quotient rule. Okay, so make sure you know how to apply all of these into like any function. Especially make sure you don't forget the chain rule, okay, because in the test and in the quizzes, I usually see that people just like take the derivative by using the power rule, but then they forget the chain rule, so make sure you keep that in mind too. Okay, so far we primarily encountered this problem given a function finds derivative, right? So this is what we have to find so far. But for chapter 5 and so on, we're gonna have to do the reverse version of it. Okay, so many important applications of calculus involve the inverse problem. What does it mean? It means that they're gonna give us the derivative of the function, and our job is to find the original function. Okay, so we have to reverse the whole process. That's why, like, another thing in here, if you want to take note for this one, originally we learned about derivative, and in this chapter we have to reverse the process. That's why we call it the antiderivative, to reverse the process of taking derivative. Okay? And then the verb for it is like integral, so we integrate it to get the integral of something. Okay? So now let's talk more in depth about the integrals or the antiderivatives. Okay, so as a warm-up in here, antiderivatives notation for them, right? So then we have, okay, let me like give you a question for just warm-up. So say, assume that we have the derivative equals to 2x, right? So then what would be the original function if you were to guess, right? And is that unique? Are there like more than one function that gives the derivative of 2x? Well, let's think about it, right? Like, what kind of function will give you 2x when you take the derivative, right? Like, my guess would be just like, okay, so if I were to give something like, I don't know, like f equal to 3x, then the derivative of this is 3, right? So that doesn't like match out with 2x, right? So I know that, well, if you notice, the power in here is going down by 1, right? So reverse that, the power has to be going up by 1, right? So instead of doing x, let's try x squared. Okay, so then let's see if we have like something close to that. So say, if I were to guess, I'm going to guess the original function to be like, I don't know, 3x squared. But then when I take the derivative of it, it equals to 6x, right? But then again, 6x is not 2x, right? Like, we're looking for 2x. So what should I do? But if you compare them, right, like they're only like 3 times by different. So let's divide that by 3 and try out if it works, okay? So then let's not talk about 3x squared. Let's only talk about x squared. That's just, you know, like try and error. And then when you take the derivative of x squared, you have 2x, right? That's like amazing, right? So f of x in here, it is x squared. This is the function that we want to find, right? But is it unique? Well, if I were to give you another function, say, I don't know, like f of x equal to, I don't know, x squared plus 1. What is the derivative of f in here? It's also at 2x, right? Because the constant, the 1 in here, it goes down to 0. And say in another scenario, if I were to give you something like, I don't know, f of x equal to x squared minus 5, the derivative of this function is also 2x, right? Because the negative 5 in here is going down to 0, because again, negative 5 is just a constant, right? So as you can see in here, f of x is not unique, right? Like there can be like a lot of version of f of x in here that gives you the same derivative, right? Like the derivative in here is 2x, and here is also 2x, and in here is also 2x. But your functions are different, right? Like the first one in pink is like x squared plus 1. The second one is x squared minus 5. And then the one in blue is just x squared with no constant. Or if you want to think about it, the constant in here is 0. Okay, so to answer the questions in here, let me put it in green. Is it unique? Well, no, it's not unique. Okay, in fact, we have like a lot of them. Okay, so how can we know exactly what function it is, right? Because we're looking for that one original function, right? I'm going to show you a machine to do that. We call it the integral. And the symbol for it would be like this, the integral sign. So it looks like the sum. So it looks like an S, but you know, just like, you know, not as curvy as our S. And okay, so this operation of determining the original function from its derivative is the inverse operation of differentiation. It's called anti-differentiation, right? So if you remember, differentiation is used for derivative. So anti-differentiation is used for antiderivative. Okay, a function f is an antiderivative of a function f. Like we have big F and we have like small f, right? So then big F in here is for antiderivative, and then the f in here is for original function. Okay, if for every x in the domain of f, it follows that f prime of x equals to f of x. Okay, so what does it mean? It means that, well, the original function, okay, how should I say this? Okay, let's talk about this example in here in blue, I guess. Okay, so if you notice, this in here is the big F. And then this in here in, I don't know, purple is a small f. How do I know that? How do I confirm that? Well, I know that f prime in here, it equals to x squared prime equals to 2x, which is little f, right? So I know that f prime, like big F prime, equals to little f prime, little f. So based on the definition, these are the antiderivative, and then the other one is the original function. Okay, I'm not gonna ask you too much about the notation in here because I know it's like complicated. Like sometimes like the little f is the original function, and some other time the little f is the derivative. So I'm not gonna like ask you guys too much about like which one is which. But when you guys get to like the practice, it'll make more sense. Okay, like the names in here are not so important, but the key thing in here is about the procedure of how to get the original function. Okay, so let me take all of these away before it confuses you any furthermore. Okay, so then if big F in here is the antiderivative of the little f, then f of x plus c, where c is a constant, is also antiderivative of x. Okay, so this is the idea of like the example that we did. We can add like a constant to the original function of like f, and it wouldn't change anything because we all know that the derivative of any constant equal to 0. Okay, so then eventually this constant here, when we take the derivative of it, it cancels out to 0. So that's why we can add any constant to the original function that we want to. Okay, and thus the process of anti-differentiation does not determine a single function, but rather a family of functions. Okay, so we call all of these the family of x squared, right? Because the simplest one is x squared, and then there could be more complicated version as like x squared plus 1, x squared minus 1, x squared plus 5, x squared minus 500, and so on, right? You can like plug in any random constant in there as you want to, but sometimes it also depends on the problem. But we're gonna talk about it in the future sections, not in this section. Okay, and then each of them differs from others by a constant, right? So as you can see, the only thing that's different between the three functions in here is the constant, right? So this one has 1, the other one has 5, and the last one, it doesn't even have anything, which means that the constant in the blue function is 0. Okay, now the anti-differentiation process is called the integration, right? Because this one is like long, that's why we usually go by integral or integration. Okay, so how to do it? Well, an integral always have 3 parts. Okay, we have the integral sign, we have the function or the integrand, and lastly we have the differential. And if you notice, to shortcut for differential we use d, right? And then the variable that we're talking about that we're using is usually x. That's why we put them together as dx for differential of x. Okay, and then this is the answer. Okay, so remember, we're not just gonna get one function, we have a family of functions. That's why it's not just f of x, but it's rather f of x plus c. Okay, the left hand side of integral f of x dx is the indefinite integral. So what do I mean by this? I mean like this part in here, we call it the indefinite integral. Like you can soon know about a definite integral, but a heads up in here is that usually we're going to have some numbers on top and on the bottom of the integral. If we don't have it, we call them indefinite, and if we do have some numbers on top and bottom of the integral sign, we call it definite integral. Okay, but again, I'm not going to test you guys too much on the terms in here, so as long as you got the outer word, that'd be fine. Okay, and it denotes a family of an antiderivatives of f. So what does it mean by family? It means that you're always going to have a c in there for like different constants. Okay, and the symbol denotes the antiderivative of f with respect to x. So this is the idea about like d of x, right? Like d is for differential and then x is for the variable that we're using. Just as a simple dy dx denotes the derivative of y with respect to x. Okay, integral notation for antiderivatives. The notation integral f of x dx equals to big F of x plus c, where c is the arbitrary constant, means that f, big F in here is an antiderivative of f. Okay, and that is this definition that we learned. Okay, so to demonstrate more about it, let me write like a quick example for what all of these saying. Okay, so let's talk about this function here in blue. Okay, so we know that, okay, how to say this? Okay, the derivative of x squared equals 2x, right? So that means that by definition, by this definition in here, x squared is big F, and then 2x is little f, right? So from here, two things that we learned. Big F prime equals to little f, and also we don't know that the antiderivative or the integral of f of x dx equals to f of x plus c. Okay? So like in practice, what does it mean? It means that derivative of x squared equals to 2x. At the same time, it means that the integral of 2x dx equals to x squared plus c. Okay, and this is the answer that we're looking for, because usually you're gonna give like the antiderivative, and our job is to find the original function. Okay, and as you can see, the original function in here can be a lot, right? It's not just one original function. They're like a family of original function. Okay, so this is about like the definition and the relationship between the two equations that we just learned. So more examples in here. Since the derivative of 3x squared equals to 6x, then the antiderivative or the integral of 6x dx equals to 3x squared. But then more, right? We need a family. That's why we have to attach plus c in there. Okay, and then let me just get rid. Okay, actually, you know what? Let me just write these in red, so that you don't get confused between the notation and the note. So this is 6x, and this one is like 3x squared, but then make sure you have plus c. So let me put it in green to catch your attention. And then similarly, for the second example in here, the derivative of 4y equals to 4. Hopefully we all know how to do that. So then the integral of 4 dy equals to 4y also. But then remember, when we take the integral, it's not just one function, it's the family of functions. That's why I have to attach the plus c in there. Okay, and just a really quick like reminder in here. Okay, for this procedure, you don't need any c, right? But for the other way, you do need a c. So let me highlight it, and you only need the c when you talk about integral. Okay, and then another thing to catch your attention here is that notice that the variable used in the first example is x. That's why we have dx in here. But then for the second example, we use y, right? So then the variable that we had in here is y, and then the answer is also has y, right? While the first example has x in the final answer. Okay, so make sure you use this the correct variable in the test and in the homework. Okay, so it's not always just x, right? Sometimes it could be t, sometimes it could be like y, w, x, y, z. Like a lot of variable can happen. Okay. All right, let's talk about our first objective of today. Finding the antiderivative. The inverse relationship between the operations of integration and differentiation can be shown symbolically by this. So differentiation is the inverse of integration. Okay, so that means that differentiation, okay, let me highlight this one, I'm in red. Differentiation is whatever that has to do with like d, right? And then the derivative of it equals to just the inside. So if you notice, dx is canceled out with the integral, right? And then like the inside of it, it is like exactly what we have as a final answer. Okay, and another thing that usually a lot of people forget is that the dx. Okay, if you do have the integral, you have dx. If you don't have the integral, the dx will be automatically just canceled. Okay, and then the other way around, we have integration. So let's do this one in pink. Integration is the inverse of differentiation. So what does it mean? It means that blue. Okay, so first of all, when you take the integral together with the derivative, they will cancel out, and then you have the same function. Okay, But then to compromise for the missing of the integral, the dx will have to be like canceled out, right? But I told you guys, like, if we start with an integral, then we must end up with the family of functions. So if whenever we start with an integral, then the answer must have c in there. Okay, but if you don't start with the integral, then the answer doesn't have to have c. Okay, so this one, the second line, we have c, and it's like a big key point. So if you don't remember to put a c in there, you're gonna get points out for it. Okay, but then the first function, there's no c in here. Okay, so make sure you can tell the difference when to use c and when not to use c. Okay, and then this inverse relationship between integration and differentiation allows us to obtain integration formulas directly from differential formulas. Okay, so these are the rules coming from like the inverse of all the set of rules that we learned from for derivatives. It's gonna be like confusing a little bit at first because like, you know, it's just too much formulas. But trust me, after you did, I don't know, like 20 problems of this style, of this type, it'll be like faster for you as like speed, and it'll make more sense at the end. Okay, so let's get to it. So the first one, the integral of k is kx. Okay, so originally you just have like a constant, then you're gonna pop out an x. Okay, and then for the constant rule, the k would be brought outside, just like how we take the derivative with, you know, like 2x. Then the 2 will be brought outside, and you're focusing on taking the derivative of x. Okay, and sum of difference, it's just like splitting them out, right? Like originally you start with one integral for two functions. Later on you split it into two integrals for each function. Okay, and then the last one is simple power rule. Okay, so this one is a reverse procedure of what we have learned. Okay, so if you remember the example that we learned, x squared derivative of it is 2x, right? So how can we get from 2x to x squared, right? We have to do the integral of it, right? So when you write an integral, make sure you attach dx at the end of it, okay? Or else it's not gonna make sense. And because we're talking about integral in here, so we must have a plus c in here. But then, have you ever wondered how we get from 2x back to x squared? I mean, like this procedure, it makes sense, right? But how can we do it inversely, right? And the reasoning for it is this. Think about it like this. X originally has like power 1, right? And then you pop it out by one more, so it's going to be like x to the 1 plus 1. Okay, and whatever new power you get in there, you're going to divide by the same number. Okay, so then this one, it gives us x squared over 2, right? And then let me put it in blue. This 2 in here will be brought outside. Okay, so at the end, you're going to get something like 2 in here, just for that 2. And then you're going to get that 2, and then you cancel it out of 2's. That's why you end up having x squared. Okay, so derivative, you have to minus the power by 1, but for integral, you have to add the power by 1 to obtain a new power. Okay, make sure you don't like get them mixed up, because I've been there. Like I used to mix them up all the time, so make sure you don't do the same mistake. Okay, in general, if you start by having some like power on x, make sure you add that power by 1 to create a new power for it, and you divide by the same number that you get for that new power. Okay, so if I were to give you some advice on what rules to focus in here, well, it would be the constant rule and the power rule, because those two are super useful, and you almost see it like every time in this class, or even in the test or in the quizzes. Okay, so let's talk more about the symbol of it. Alright, so for example, if we start having like 3x as an integrand, well, what do? First of all, we're going to bring out a 3, right? Because what is 3? 3 is a constant, right? So we're going to bring it out. We're going to bring it out. And then we know that x is just x to the first power. So then next step, we're going to add 1 by 2. I mean, add 1 by 1. So then we're going to get x squared. But then the new power that we have to divide out. So then we're gonna have a 2 on the bottom, and then we multiply everything together to end up having 3 over 2 x squared plus c. Okay, if I were to do it like my way, here, let me show you another version of this. So I start with the integral of 3x, and to compromise for the integral, simple, I always gonna have like dx, right? And after that, I pull out a 3, just like how we do it. And after that, I take the integral for it. So I'm not gonna do the integral sign anymore, but like to compromise for it, the power with it will be changed, right? Like I would have to put new power for it. So it's gonna be like 1 plus 1, and then on the bottom I divide it by the same thing. And make sure when you like make the integral disappear, you have to compromise it for by putting a c to it. Okay, so at the end it's gonna be 3 over 2 and then x squared and then plus c. That's the same answer that they have. Okay, so let's talk about my work in here. I know this looked like way harder than this like example in here, but trust me, it's not gonna be that bad. Okay, so first of all, we all know that x squared of x is actually x to the 1/2, right? So let's rewrite them out. So a quick reminder is that remember back in the day when you have like 1 plus 2 divided by 3, we can split it out as 1 over 3 plus 2 over 3, right? So then we're going to do the same thing in here. We're going to have x divided by x to the 1/2 plus 2 over x divided by 1/2 and then dx at the end for the integral symbol. Okay, so if you need something for like reference, make sure you refer to this example in here, because we all know that we love numbers rather than, you know, variables, right? So now let me talk more about the procedure in here. Okay, so by the sum and difference rules, I'm gonna split it out into two integrals. So it goes like the integral of x divided by x to the 1/2 dx plus integral of 2 divided by x to the 1/2 dx, right? Okay, what do I do next? Well, I'm gonna simplify it, right? So this equals to okay, so we all know that x is like x to the first power, right? So then let me just put it in blue to like emphasize that. And then we're gonna combine them. So then x to the first power divided by x to the 1/2 power, because we have like division in here, so we're gonna subtract them, and then 1 minus 1/2 is just 1/2, right? So we end up having x to the 1/2 in here, and then dx. For the second one though, well, because 2 is a constant, so I'm gonna go ahead and bring it out. So it looks like 2, and then on the inside I'm gonna get 1 divided by x to the 1/2 dx, right? And then next up, what do? Well, we all know that this, we cannot do anything with the derivative or antiderivative of it, right? Because we don't have anything like 1 over something. So instead of having like 1 over x to the 1/2, let me rewrite it in like x to the something form, right? And how can I write it? Well, I'm just gonna flip it, right? So that means, let me erase this one. And how can I flip it? Let me put it in green. It's gonna be x to the 1/2, but then in negative because I'm gonna flip it. Okay? And now the integral, the key one in here, let me put it in orange. How can I take the integral of this? Well, so in here I'm gonna get x to the 1/2 plus 1, like all in the power, and on the bottom I'm gonna do the same thing, 1/2 plus 1. And then for the outer fraction, I have 2 on the outside times x to the negative 1/2 plus 1, and then on the bottom I'm gonna have the same thing, negative 1/2 plus 1. And to compromise for the missing of the integrals, I'm gonna put a plus c at the end. Okay, so it's gonna be like plus c in here. Okay, and now the final answer. So it's gonna look like, what is it, 1/2 plus 1, I'm gonna get like 3 over 2, so flip it, it's gonna be 2 over 3, and then the power in here would be 3/2. Okay, and then the outer number, the bottom in here, if you were to put it in the calculator, you're gonna get 1/2, right? And if you were to flip it, because it's on the bottom, you're gonna get a 2. So 2 times 2, we have a 4. Okay, so let me take this thing out. Actually, you know what? Let me just do it step by step, just in case like I confuse you guys. Okay, so this one is gonna be x to the 3/2 divided by 3/2 plus 2 times x to the 1/2 divided by 1/2 plus c. And to end this thing, well, because this one is on the bottom, so I'm going to go ahead and flip it. So it's going to be 2/3 x to the 3/2, and then plus, this one is on the bottom, so I'm going to go ahead and flip it again. So I'm going to have a 2, but on top of that, I also have another 2, right? So that means I'm going to have a 4 in here rather, because this 2 and that 2. Okay, and then this is like x to the 1/2, and at the end I'm going to have a plus c. Okay, so this is it. If you don't want to write as like a power form, like me, then I usually gonna do it in like the root form. So the root form for it is gonna look like, what is it? Square root of x cubed, because the top part is for the power on the inside, and then the bottom is for the root, and then the other one is 4 square root of x and then plus c. Okay, so I would prefer this one over the other answer. Okay, but in the test, if you stop in here, I'm not gonna complain about it because like it's hard enough already. Okay, and for your part, you're gonna have this one. Okay, and just a heads up, for your part, you have to split it out into the integral of something over something, and then plus something over something, and then dy. Okay, and make sure you're using the variable of y, not x anymore. Okay, so watch out for the integrals. Okay. And now, the next objective, particular solution. Okay, so we know that the equation y equals to the integral of f of x dx equals to big F of x has many solutions, right? Because of that, like plus c at the end. We can have something like plus 1 at the end, or like -5 at the end, or even like 0 at the end, right? Because it can be like any constant, and then it's gonna give us the same derivative, right? And then each of them different by a constant. This means that the graphs of any two antiderivative of f are vertical translation of each other. Okay, so say if we were to take the derivative of this function right here, well, how do we do it, right? So here, let me put it in here really quick. So first of all, I'm gonna like split it out into two integrals. So I'm gonna have like the integral of 3x squared dx minus the integral of 1 dx, right? And after that, I'm going to bring the 3 outside, so it's going to look like 3 integral of x squared dx, and then minus 1 in here, and then on the inside, you don't have anything, right? But then we do need an x, right? And because we don't have anything, like we don't have any x, so I'm going to write x to the 0 power. Okay, so let me put it in another color, because this one is like a big key point that everyone like usually get confused once a while. Okay, and this is my 0. Let me write better. There we go. And then next up, we're going to take the integral for it. So let me change it to orange. The 3 on the outside, I'm going to keep it on the outside, but then the x squared is going to be 2 plus 1 in here, and we divide it by the same number. And then the 1, I'm going to keep it outside, and then x to the 0 plus 1 in here would be 0 plus 1, and at the end I'm gonna have a plus c, right? So let me try to squeeze that in. Okay, it's not working, so plus c, there we go, it's better. And now what do we do? Well, we're gonna have a 3 in here, and then this one will be like x cubed over 3, and the other one will be like 1 divided by x to the first power divided by 1 plus c. We notice that the 3's in here cancel and the 1 in here can also cancel, right? So the final answer would be like x cubed minus x plus c. Okay? Which is the exact same thing that we had earlier. But then remember, oh, I forgot a plus c in here, by the way. And yeah, there's a plus c on here too. Because we talk about family of functions, not like any particular function, right? Okay, so just imagine if the c were to be 1, then you're gonna get this function right here. It's like it's cut out by a screenshot already, but yeah, just imagine it's there. Okay, so let me change the color for it. So when c equals to 1, you're gonna have this function. Okay, and if this c equals to, I don't know, like 2, then you're gonna have this function. And I think I mistranslated. For c equals to 1, I think it's the upper function, so let me correct myself for that. And how do I know that it's this function? Because it's hitting through 1, right? And then at 2 is hitting through 2. This one, and similarly, if my c equals to 3, then I'm going to have a curve at 3, right? Where it hits 3. And lastly, if I were to have something like c equals to 4, then I'm going to have this curve in here where it hits 4. Okay? So similarly, you can try yourself with this example to see if you're going to have the same thing as what I did in here. I'm not going to ask you to do it for your part, but this one is like a similar example for that. Okay, so first of all, we're going to split it into two integrals, and then you're going to have like two answers for each of them. Okay, so then for the real example of ours, find a general solution of f prime of x and find a particular solution that satisfies the given initial conditions. Okay, so how can we do it, right? So first of all, we have a function, and before that, let me just cut everything in here down so then we have more space to do the work. Okay, red. Okay, so we have a function in here to take the integral, and we also have a condition, right? So this one is what I call by initial condition, and you'll be able to tell it right away because it doesn't have any like variable with it. So whenever you're given like a piece of function with like just values, like just numbers, you know right away that we're talking about the initial conditions. It's not like the function where you have to take the integral or anything, okay? It's just a condition, okay? So let's get into the work in here. So on this section, we're gonna start with the integral, and we're gonna go ahead and copy and paste out a function in here. And after that, we compromise the integral by writing dx in here, right? And then what do I do after that? Well, I'm going to split it into two integrals just like usual, right? So I'm going to have square root of x and then plus 1 divided by 2 square root of x and then dx, right? Okay, for the first one, I'm going to rewrite it x to the 1/2, right? Because of the square root. For the second one, I'm going to do it pretty fast. Oh, okay, let me do this slow, actually. So I'm going to bring out a 1/2 in there. So on the inside, I'm just going to get 1 divided by square root of x dx, right? And then let me go ahead and copy and paste the first equation down here. But then on the second equation, though, it's going to look like x to the negative 1/2. And let me change the color for this one because I think it's important. Okay, so this one is like plus 1/2 integral. But then the other one in blue, it is x to the negative 1/2, and then back to dx to compromise for the integral. Okay, and just in case you guys curious, what do I mean by the blue part? I'm talking about this one in here. Okay, if you notice, if it's on the bottom, we must have the negative on the exponent or on the power, right? So then the next step, orange, taking the integral of it, right? So we're gonna do x to the 1/2 plus 1 for the new power. And we divide it by the same number that we just had for the new power. And for the second one, we have 1/2 on the outside, and then we're going to do the same thing. So we have x to the negative 1/2 plus 1, and then divided by negative 1/2 plus 1 on the bottom, and then at the end we have a plus c, right? And then as you see it, and as you already saw it in the last example, so I'm going to fast forward to this, the bottom in here is 3/2. After you flip it, it's going to be 2/3. Okay, and a new power in here is like 3/2. Okay, the number on the bottom in here should be 1/2. After you flip it, you're gonna have a 2. The 2 canceled out with the 1/2, so I'm just gonna have a 1. That's why I'm not gonna write anything for it. And then the new x in here, it is x to the power of 1/2 and then plus c. Okay, and again, I told you guys I really hate it when I have like power form, so I'm gonna rewrite everything in the root form. Okay, so I'm going to have x cubed and then square root of it, and then the other one I'm going to have square root of x and then plus c. Okay, let me move this one a little bit up. And this is my final answer for the general form, right? But if you guys notice, we haven't talked about this guy yet, right? And there's a reason why for it. Okay, let me put it in green. Okay, let's talk about this one in here. What do we do with it? Well, we're gonna try to solve for c, right? So the inside here, it is x, and the outside here, it means a function. Okay, so what does it do? It tells us that if we were to set this whole thing equals to negative 5 and plug in 0 wherever we have x, what would be c? Okay, so let me do it really quick in here. Square root of 0 and then plus c. Okay, so if you notice, 0 times anything will be just 0, right? So I'm not going to have anything for that or that. So at the end, c in here equals to negative 5, right? So let me also box this one because it's a key point. And then the final answer, like the final answer of this question, we're gonna have f of x, because the question is asking us to do it. The general solution of f prime in here would be, just f of x. Okay, equals to, I'm gonna go ahead and copy this one down, but then replacing c by -5. So it goes like 2/3 square root of x cubed plus square root of x minus 5. And this is it. So in a test, you don't have to box like everything, but then this is the final answer I'm looking for. Okay? And as for your part, you're gonna have to do this one, okay? And remember the pink one in here, the condition in here, you only apply it to if I see. Okay, so let me like point it out really quick in here. So this one is used if I see, so that you can write your final function with no like variable except for x. Okay, and this is the part what you have to do for the integral. Okay, and now last objective of today, application. Okay, so how can we apply it in like real application, right? So in chapter 2, we use the general position function, neglecting the air resistance for a falling object to get like like the distance function or the position function, as I mentioned before. And here's the formula for it. And in fact, you don't have to remember it unless you take like physics class or anything like that. But for a business major, I don't think you have to remember this formula even. And I'm not going to test you guys on this formula too, so you don't have to memorize it. Okay? And S in here is the height in feet, and T in here is the time in second. Okay? And we use differentiation to derive the velocity function and then the acceleration function from the distance function. We can use integration to derive the velocity and then the distance function from acceleration function. In other words, differentiation or taking the derivatives, we have distance function, and then from there we get the velocity function, and then keep taking the next derivative, we're gonna get acceleration. Okay, but then for integration or taking the integrals, we start by having the acceleration function first, and then we take the integral of it to get the velocity function, and then we're taking the integral of the velocity function to get the distance function. So you remember, if you notice, like everything in here will be reversed, right? Like whatever we have first, that will be whatever we find first on the outer procedure. Okay? Anyways, let's talk about the real application for it. Okay, so for my part, I have the rate of growth of the number of internet users is modeled by this equation, where t is equal to 1, corresponding to the year of 1991, and the number of internet users in 2004 was 863 million. Okay, so as you can see, there's an equation, and there's like some other numbers that we have to focus on, right? So let's put this one in green actually. So we have a function in here. And we also have some condition in here. Okay, so the easiest thing for me usually to write out is the initial function or the initial condition. So I would know that usually I'm gonna call it big F, but in here they call it I for internet users. So I'm gonna go for it and just use I for internet users. Okay, so I of 4 equals to 863. And if you guys still don't know why, it's because t equals to 1 represent the year of 1991. Actually, it's not even like 4. Okay, I thought it's like 2000 for some reason. Okay, let's do the math in here. So 2004 minus 1991, so that would be like a 3 in there, right? So then this one is actually like t of 3 equals to this number. Okay, here's a better way, because I feel like I confused myself with the math. So let's list them out really quick. T equals to 1 if we're talking about the year of 1991. So when t equals to 2, we're gonna get 1992, and then 3 equals to 993, and then so on. And then when we get to like 2000, we're gonna get like 10. So then when we get to 2004, we should get 14, right? And if I think I messed up with the math earlier, that's why I got like just 3. But yeah, anyways, we're gonna get 14 for the year of 2004. Okay, so it's not 3 in here. This one is 14. So let me just put in red, just so you guys don't make the same mistake as I did. Because if you do like 2004 minus 1991 in there, then I believe you should get something like, I don't know, like 13. But if you notice, that's not the case in here, right? So watch out for it. Like, be careful for that, okay? And now, let me take that out. Okay, talking about the real work in here for the integral, what do we do, right? So we have a function already. That's good. We're going to take the integral of that. So the integral of that whole function, let me just copy and paste them down really quick in here. T plus 332 t squared minus 19.34t plus 21, and then dx to compromise for the integral. Okay, I'm gonna combine like 2 steps in one, okay? Because it's like really long equation to keep rewriting. Okay, so first step, I'm gonna break this function into 4 parts: 1 part, 2 part, 3 part, and 4 parts. Okay, and after that, I'm gonna pull out all the constant in front. So it goes like negative 0.25 integral of t cubed dt, and then plus 5.32 integral of t squared dt minus 19.34 integral t dt, and then lastly plus 21.03 nothing. So we're gonna have like t to the 0 and then dt. Okay, and I think this one is supposed to be a t, not an x, but then it's just, you know, habit. Okay, so how do we do it? Well, in short, we're just gonna have something like negative 0.25 in here. It's gonna be like t to the 4th power divided by 4, and this one is mine like times, so let me make it bigger a little bit. And then this one is 32 times t cubed divided by 3, and then minus 19.34 times t squared divided by 2, and then this is 21.33 times t to the 1st power divided by 1, and then plus c for the missing up all the integrals in dx. Okay, and now, okay, that's a lot of work. All right, let's put it into the calculators to simplify the negative 0.25 and the 4. And with all of that, you're gonna get negative 0.75 t to the 4th power plus 10.64 t cubed, and then give me 1 second, let me get on my calculator too. Okay, this is not like the same number as I got. So this one is supposed to be 1.77. Okay, and then what else? This one is supposed to be 19.34 divided by 2. That is 9.67 t squared. And then, okay, I think this number is wrong too, so let me double check really quick. I'm gonna do 0.25 divided by 4. That is, okay, this is an ugly number. 0.0625. Okay. Usually I do it by like 2 decimal places, but if you want to be like more accurate, you can go for more decimal places. Okay, and then this one is 21.03 t and then plus c, right? Okay, now how we do all that? Well, we're gonna assume that all of this equals to a 63, just like what we had earlier in pink. So let me go ahead and use this piece of information down here. Well, this is that one down here. So we start by writing a63 equals to negative 0.0625, and then we talk about 14 as a year, right? So we're gonna plug in 14 for t to the 4th power and plus 1.77, 14 to the third power, and then minus 9.67, 14 to the second power, plus 21.03 times 14, and then plus c at the end, right? So if you do, after you did all that work, now we have to solve for c, right? So let me get it, plug it into my calculator really quick to see what c is. 625. Sorry for the waiting time. Okay, so after I did all of that, I got c equals to 8.02. And correct me if I'm wrong, okay? Because this is a long calculation. And I think I might like make some mistake or something. So anyways, the final answer, let me put it in blue. The I function, or the internet user, it equals to this function. And then we have to replace it by c equals to 8.02, right? So it goes like negative 0.0625 t to the fourth power plus 1.77 t cubed minus 9.67 t squared plus 21.03 t and then plus 8.02. This is it. This is the final answer of ours. Okay? And as for your part, you have to do something similar to that. So this. And just a heads up, you're also gonna have a function to take the integral for. And as you can see, your examples are like similar than me, like mine, much simpler than mine, because you only have 2 terms to do. And then if you're confused for what we have for the initial function, hopefully you have the same thing as I do in here. The cost function in here are producing 200 units equals to 40. So you should have something like this as for your initial function. Okay, if you don't know how to extract this function from the given values, let me know. Okay, like just make sure you ask me right away, because this one will show up on the exam too, and even on the final too. Okay, so anyways, this is it for today. Thank you for your listening. Take care and have a great day. Bye bye.